So now we want to try to apply what we've learned about vector valued functions to some real life applications. And of course, one of the first real life applications that we have applied every aspect of calculus to that we've discovered is projectile motion. That's because Newton, Isaac Newton, was interested in projectile motion when he was inventing calculus in order to be able to do the math that he wanted to do for the physics that he was interested in. So you have to remember that calculus 1, 2, and 3, are to a great extent the servants of physics in that respect. So when we do application problems, we're very much interested in motion. Now, in Calc 1 and Calc 2, we could only do straight line motion. So we did a lot of falling objects, and that's because we only had two variables to work with. We had time, and then we had distance, and that was it. So if you remember, you have a lot of, you are standing on a cliff, and you throw an object straight up in the air, and then it falls straight down, and there you go, right? Falling object problems. And of course, in Calc 3, we won't be limited by that. And that's what this section's all about. We're going to expand upon all of that. But first, we're going to spend a little time reviewing a Calc 1 falling object problem, since this is the basis that we will be building on. Okay, so we have an example right here. A person standing on a high cliff holds a rock just over the edge of the cliff and throws it straight up. There it is. That's how you can tell you're in a Calc 1 or Calc 2 problem, because they're going straight up, because that's all you had at that time. The height of the rock after t seconds is given by this. So this is the position function right here. All right, so the height, find the height, velocity, speed, and acceleration of the rock. All right, so the height, aka the position, right? This is just height because it's a falling object function, is s of, oh, and we want it at 2 seconds, if everybody sees over here. We have the function, so we want it specifically at t equals 2. All right, so I want s of 2. S of 2 would be negative 16 times 2 squared plus 48 times 2 plus 160. And I have Desmos and or Maple to find that for me. Now I could do this a couple ways. I mean, I could just type that mathematics in and it'd be fine. But I'm figuring I'm going to need this for later. So I'm going to name my function S1 because it's example 1. And so then I'm going to name this S1 colon equals. Then I hit enter, and so it stored that function. Oh, and it doesn't like the parentheses. That's right. Okay, so hold on. S1, there we go. So then S1, I want to sub. So I want to sub into S1, and I want to sub in t equals 2. So let's go to Maple. So I'm going to name my function S1 because I figured this is not the only position function I'm ever going to need in this particular set of notes. So S1 for S for position, it actually stands for like situation. It's Latin. 1 because it's example 1. And I named my function. Okay, so there's my function S1. Now, to make it so that it substitutes a value in, I can't just use function notation. Maple unfortunately does not know what function notation is, so I have to use the eval command. I want it to evaluate S1 at the value t equals 2. And when I do that, it will give me 192. Okay, so eval is a nice command to know, especially if you've named your function. So I find that it is equal to 192. And of course, because this is height or position, this would be in feet. All right, now let's find the velocity. The velocity is the derivative of position. So velocity is s prime of t, which is s prime would be negative 32t plus 48. So the velocity at t equals 2 is negative 32 times 2 plus 48, which is negative 64 plus 48, which is negative 16, and that would be feet per second. Now, if you're thinking, could I get Maple to help me? Well, sure, right? Of course you could. So if I want the derivative of S1 with respect to t, There you go. There's the velocity. I can name it v1 colon equals, so it knows that. And then I could say eval v1 at t equals 2, and there you have it. Negative 16, just like I said it would be. Sorry, that's probably pretty small font. Let me make it bigger so you can see it. Okay, lovely. So now what about the speed? Well, the speed is the magnitude of velocity. So it will just be the magnitude of that answer. So I could say, find me the label, which was 1.4, and then find me the magnitude of that. Oh, whoops, I'm not in linear algebra. Hold on. I just want the absolute value of it. Let's see if it'll do it. There we go. So it wasn't double, we're not in vectors, so sorry about that. So just put absolute value signs because that would be the magnitude. All right, so that's what I'm about to write. Speed is the magnitude of velocity. So it's the magnitude of s prime, and therefore at t equals 2, my speed would be the magnitude of negative 16, i.e. the absolute value, which would be 16 feet per second. Right? If velocity is negative, because velocity is speed with direction, then the speed is 16. All right, what about acceleration? Well, acceleration is the derivative of velocity. So a of t is the derivative of velocity, which is the second derivative of position. All right, so that would be, the derivative of velocity would be negative 32. And that would be feet per second squared, because we differentiated with respect to time twice. So that's why it's secant squared. All right. Now, what about the maximum height of the rock? Well, the maximum height happens when there's a local max in the, or a critical value, if you will, in the position function. So the maximum height happens at a critical value, which happens when the derivative of height, which is s prime, i.e. the velocity, is equal to 0. So I would set negative 32t plus 48 equal to 0, and I would solve for t, which will give me 1.5 seconds. So that's when it happens. But that's not answering the question. They actually want the height. So the max height is position. So that would be s of 1.5, which would be negative 16 times 1.5 squared plus 48 times 1.5 plus 160. And of course, we're going to make technology do that and come up with a number for us. But I can tell you it'll be feet because it's height, and height is a distance thing. Now first I want to show you that I can use the solve command to find my time. So I can say, hey, solve this for when v1 equals 0. Set that velocity equal to 0 and solve it for t. And it does. It finds that it's 3/2. And of course, we know that the approximation for 3/2 is 1.5. And if I want to come up with a decimal, I could probably trick it into putting in decimal places along the way. And sure enough, there you go. It gives me a decimal place. Lovely. There's also the approximate feature that you can get out of the math editor. All right, then I want to find s of 1.5. And you can't just write s of 1.5. Like, it doesn't know what you want. So you have to use the evaluate command, eval. And I want to evaluate s1 at t equals 1.5. And we get 196. So it's 196 feet. That's the maximum height. Now let's find the time of flight and the velocity at impact. Okay, so the time of flight, so that's the time that it takes to hit the ground. So what we're really interested in is the time when it hits the ground, because we know that it's going to start at time 0, so I'm not really worried about that. All right, so time of flight. When it hits the ground, so what we're really saying is the time when s of t equals 0. Okay, so that means that we really want negative 16t squared plus 48t plus 160 equals 0. Now, of course, we could do this with technology, but it doesn't hurt us to do a little bit of algebra 1, because negative 16 factors into all of those things. And then this is factorable. This is t minus 5t plus 2. And therefore, right, t minus 5 is 0, or t plus 2 is 0. I'm just going to do a full review of algebra here. T is 5, or t is negative 2. And since you can't go back in time before you threw the rock, that's out, right? So that's not possible. So this is our answer. Now, could we do that in Maple? Of course we could. Right? It wouldn't even be that hard. Right? So we would use the solve command. So we would say solve for s1 equals 0 for t. And I'm going to want a decimal approximation, so I'm just going to put the 0.0 right in there. Enter. And there you got your two answers, negative 2 and 5. Right? So I think this one would have worked out no matter what I did. Yeah, negative 2, 5. No problem. And then make all these bigger. So there's my two solutions that I just found by hand, but I can prove that I was correct. Okay, so now there was another question. What's the velocity at impact? So that's the velocity at the time when it hits. I think it was a rock. When the rock hits the ground. Well, we just found when it hits the ground. So that's the velocity at 5. So we're just going to take negative 32 times 5 plus 48, which is what, negative 160 plus 48, so negative 112. But of course, I can make Maple do this. So I can say evaluate, right, because I'm trying to substitute, v1, comma, t equals 5. And there we go. My mental math was correct. It is 112. Right? So that would be negative 112. And of course, it's negative because it's hitting the ground. Right? The velocity, right, it's going down. So velocity is negative. Now, before we leave this problem behind, we want to think about a diagram of what we're seeing here, just because it'll be helpful for us for the next page. So we have a cliff, and we have a person standing on the cliff, right? And they're throwing a rock straight up in the air. So right here is t equals 0, right? So they take the rock, they throw it straight up in the air. It goes straight up and then straight down. Up at the top, at 1.5, we hit the maximum of 196 feet. Then kind of along here, right, we had t equals 2. Right, this was part A. So t equals 2, we were at 192 feet. And then we go all the way to the bottom. At t equals 5, we're at 0 feet. We hit the ground at 112 feet per second. Hitting the ground takes care of the negative part, right? Or if you want, you can say it's negative 112. There we go. So before we leave this video behind, let's think about how this graph would change if the rock is not thrown straight up, but it has some horizontal motion as well as vertical. So instead of just going up and down, what if it's going out along a path? What if it's going this way? and there's motion to it, right? So instead of just going up and then down, it's going out. Okay, well then the motion would be a vector valued function, which would have an x component and a y component, because this is your y and this is your x. That's two-dimensional motion, right? So this is two-dimensional, right? It has horizontal motion, right? Horizontal motion is two-dimensional. But what if it was even worse? What if there's a crosswind? So it wobbles around and it moves side to side as it falls. Well, crosswind means we're in three-dimensional. So we would have the rock starting here and coming out and landing in one particular octant or another, and it would have an arch to it. So you'd have your x, your y, and your z, and you'd have to name or model the projectile motion with a vector valued function in 3 dimensions. So once I see that crosswind, I know we're in 3 dimensions. And we're going to have to think about for a minute how that's going to affect our velocity, speed, and acceleration. Because we're going to have to turn everything we knew for one-dimensional motion, right? How height, velocity, speed, and acceleration were related, and we're going to have to expand upon it for vector valued functions in 2 and 3 dimensions.